You have 10 fingers. That's it. That's why math exists. No, seriously. Think about that for a second. Everything. Every rocket, every bridge, every iPhone, every stock market crash, all of it traces back to some ancestor looking at their hands going, okay, so I have this many sheep. That's the origin story. That's where we start. But here's the thing. We didn't stop at fingers. We never stop. That's kind of humanity's whole deal. We take something simple, stare at it long enough, and accidentally invent the future. So today we're going to do the whole thing. All of it. We're going from prehistoric finger counting to the mathematics of folding space itself in about 18 minutes. Buckle up. Okay, so why do we even count? And what's the actual point? And here's your first brain check. Imagine you're a cave person. You have a flock of sheep. Every morning you let them out. Every evening you need to make sure they all came back. But you don't have numbers. What do? N. You grab a stick, you make a scratch for each sheep, and then when they come back, you match scratches to sheep. Scratches are left over, you're going wolf hunting tonight. That's it. That's counting. You invented it. Congratulations, you're a mathematician. Those scratches on the stick are called tally marks. Wow, and here's the wild part. We found actual bones carved with tally marks that are 43,000 years old. The Lubombo bone. Found in a cave in Africa. Someone 43,000 years ago sat there scratching lines into a baboon fibula like it was a homework assignment. And they were doing math. That's the first textbook ever written. It was a bone. So we've got tallying. One scratch equals one thing. That's the concept of one-to-one correspondence. Sounds fancy. It's not. It's just the idea that you can pair things up. One sheep, one scratch. And this is actually the foundation of all of mathematics. Not addition. Not algebra. Just the idea that one thing can represent another thing. That idea is going to come back and destroy your brain later, by the way. File that away. Now, here's where it gets spicy. Tally marks work fine if you have 20 sheep. But what if you have 300? You're going to need a bigger stick and a better system. So humans started grouping. 5 scratches, then a diagonal one through them. You've seen this. You've done this in a board game when you're keeping score. That right there is the birth of place value. The idea that where a symbol sits changes what it means. The Babylonians went absolutely feral with this around 3000 CE. They invented a number system based on 60. 60! You're probably wondering why 60. And honestly, historians are also kind of wondering why 60. Best guess? N. 60 is divisible by a ridiculous number of things. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. It's the most divisible number you can actually count to on your hands using finger joints. And yes, you can count to 60 on your hands if you count the joints on each finger with your thumb. Babylonians figured this out before the internet. Respect. And we still use their system, by the way. 60 seconds in a minute. 60 minutes in an hour. 360 degrees in a circle. You've been using Babylonian math your entire life, and nobody told you. That's kind of insane. That's legitimately insane. Okay, but here's where it gets weird. Because all this counting and grouping is great, but at some point someone asked a question that changed everything. The question was, what is 1 plus 1? N. And you're thinking, obviously that's 2, what kind of question is that? But hold on. How do you prove it? Mathematically, rigorously, no hand-waving, prove it. It took humanity until 1910 to do this properly. A guy named Alfred North Whitehead and a guy named Bertrand Russell sat down and wrote a book called Principia Mathematica. It took them 10 years. It is 3 volumes long. It is almost 1,000 pages. And on page 362, after 361 pages of groundwork, they finally proved that 1 plus 1 equals 2. They then added a note saying, quote, "The above proposition is occasionally useful." Occasionally useful. The most sarcastic footnote in the history of human civilization. So why does it take that long to prove something that obvious? Here's why. Because math isn't about what you can see. It's about what you can prove from first principles, with no assumptions. And it turns out, when you strip away every assumption, even the simplest things require enormous scaffolding to hold up. This is actually math's superpower. And also why everyone cried in middle school. Both things are true. Now we've got numbers, we've got addition, things are great. And someone asks, what is 2 plus 3? N? Easy, 5. What is 10 minus 3? 7, whatever. What is 3 minus 10? And here, everyone in ancient history collectively went, you can't do that. You can't have less than nothing. That's absurd. Negative numbers are fake. For literally thousands of years, mathematicians rejected negative numbers. Ancient Greeks? Nope. Ancient Romans? Hard pass. Even in the 1700s, some European mathematicians called negative numbers absurd and fictitious. And then someone used them to solve a debt problem. Because if positive numbers represent money you have, negative numbers represent money you owe. And suddenly, they weren't absurd anymore. They were the entire banking system. The pattern here is going to keep repeating, so get used to it. Humans invent something, call it impossible, then desperately need it, then accept it, then use it to run civilization. We're going to see this again very soon. Very, very soon. Okay, so we've got whole numbers. We've got negatives. Things seem complete. Why? And then some ancient Greek guy tries to measure the diagonal of a square with side length 1 and discovers, wait, this number doesn't fit. It can't be written as a fraction. It just keeps going, forever, with no pattern. He probably had a crisis about this. They literally called these numbers irrational. Not as a math term, as an insult. They named them after the Greek word for without reason, because they thought numbers that couldn't be expressed as fractions were against the laws of nature. One of Pythagoras' students allegedly got thrown off a boat for telling people about them. Which is genuinely the most dramatic peer review process in history. But here's the thing. The square root of 2 is real. You can draw it. Get a piece of paper. Draw a square with sides exactly 1 centimeter. Now draw the diagonal. That line right there, the one you can see with your eyes and touch with your finger, that line has a length that is irrational. It doesn't stop. It doesn't repeat. It just goes 1.41421356237 forever. Reality contains infinities that can't be written down neatly. Geometry just casually handed us that for free. Speaking of geometry, here's Euclid, ancient Greece, around 300 BC. This guy sat down and said, what if we built all of geometry, every theorem, every proof, every property of every shape, from exactly 5 rules? And just 5. He called them postulates. Things so obvious that you just accept them as true without proof. Stuff like, you can draw a straight line between any 2 points. Sure, fine. And then, from those 5 rules alone, he derived hundreds of theorems. A whole structure of flat space, from 5 sentences. The man wrote a book called Elements that was the standard geometry textbook for over 2,000 years. 2,000 years. Your calculus textbook is going to be obsolete by Tuesday, and Euclid's homework is still being assigned. And here's the wild part about those 5 postulates. The 5th one always seemed a little different to everyone. It was clunkier, less obvious. Mathematicians spent 2,000 years trying to prove it from the other 4. They couldn't. Because it turns out, if you change postulate 5, you don't get wrong geometry, you get different geometry. Geometry that works on curved surfaces, geometry of spheres, geometry of saddles, geometry of space-time. Wow, when Einstein needed to describe how gravity bends the fabric of the universe, he grabbed that non-Euclidean geometry, the thing that started as, what if postulate 5 is wrong, and used it as his entire toolkit. One weird postulate, 1,000 years of wondering, one general theory of relativity. Mathematics is patient like that. Now, we need to talk about algebra. I know. Just stay with me. Algebra is basically the move where instead of saying 5 plus 3 equals 8, you say 5 plus x equals 8. What is x? So n, you're not solving a specific problem anymore. You're solving a shape of a problem, a template. And once you have templates, you can solve an entire category of problems at once. That's not just useful. That's a superpower. The word algebra comes from Arabic, al-Jabr, from a book written by Muhammad ibn Musa al-Khwarizmi around 820 AD. You also know him because the word algorithm comes from the Latin version of his name. One guy, algebra and algorithms. He basically invented modern computing 1,200 years before computers existed. Honestly, just unacceptable levels of productivity. But algebra had a monster hiding inside it. The quadratic equation, you've seen it. X squared plus something equals 0. What is x? Sometimes you get normal answers. Sometimes you get answers that require you to take the square root of a negative number. And remember, we just said you can't have numbers more absurd than irrationals. Negative square roots? N. Impossible. You can't square any real number and get a negative. It just doesn't happen. So mathematicians in the 1500s did something incredible. They said, okay, let's just pretend you can. Let's say there exists some number, let's call it I, where I squared equals -1. We know it can't be real. We'll call it imaginary. Haha, it's fake. And then they used it to solve cubic equations, and it worked. The imaginary number, the fake impossible fiction, produced real correct answers to real problems. Every time. Without fail. And here's the moment I need you to actually stop and feel this. Imaginary numbers are used today to describe electrical current flow. Quantum mechanics literally cannot be written without complex numbers that combine real and imaginary parts. Every time your phone processes a signal, imaginary numbers are doing the work. The thing that was invented as a math joke to solve a puzzle is the thing your Wi-Fi runs on. There is no cleaner example of what mathematics actually is. It's not about what's real, it's about what's consistent. If the rules hold, if the logic doesn't break, the math is valid, and eventually, reality will catch up and start using it. The universe doesn't care whether you think the numbers are real. It's already using them. That's the awe moment. Sit with it, because here's where it connects back. Remember the beginning? One-to-one correspondence. One thing represents another thing. Tally marks represent sheep. Negative numbers represent debt. Imaginary numbers represent phase shifts in electrical signals. Mathematics is, at its core, the science of one thing representing another. And the crazier the representation, the deeper into reality it reaches. Now, things are about to get moving. Literally. Okay. We have numbers, we have algebra, we have geometry. Someone eventually asks, but what about things that move? What about things that change? Your algebra gives you a snapshot. But reality doesn't do snapshots. The moon doesn't sit in one place. A thrown ball doesn't freeze. Population doesn't hold still. How do you do math on stuff that won't stop moving? Enter calculus. And two guys who absolutely hated each other. Isaac Newton working in England. Gottfried Wilhelm Leibniz working in Germany. Both of them, independently in the 1600s, invented calculus at roughly the same time. This caused one of the most spectacular academic feuds in history. Newton accused Leibniz of stealing his ideas. Leibniz called Newton's followers biased. The Royal Society conducted an investigation into the plagiarism claim, which should have been neutral, except Newton secretly wrote the investigation report himself. The verdict was obviously in Newton's favor. It was basically both the detective and the suspect. This was the original peer review scandal, and it went on for decades, and Leibniz died in disgrace. The irony? N. We use Leibniz's notation today. You see dy ddx in a calculus class? That's Leibniz. Newton won the feud and lost the notation war. The universe has a sense of humor. So what actually is calculus? Calculus is two things, derivatives and integrals. And they're opposites of each other. Here's the physical version. You're in a car, you look at the speedometer. It says 60 miles per hour. That's a derivative, the rate at which your position is changing right now. Now you want to know, how far did you drive in the last hour? That's an integral. Adding up all those tiny speed values over time to get a total distance. Derivatives slice. Integrals accumulate. They undo each other. That's it. That's the whole thing. The actually wild insight that Newton and Leibniz both independently realized is that these two operations, slicing into infinitely tiny pieces and adding up infinitely many infinitely tiny pieces, are exact inverses of each other. This is called the fundamental theorem of calculus, and it is genuinely beautiful in a wait, why is that true kind of way. The relationship between the slope of a curve and the area under it is not obvious at all. And it connects literally everything: physics, engineering, economics, biology, every field that involves change. All of it sitting on top of this one insight. From here, math started branching into directions that look like they have nothing to do with counting sheep. Statistics, which lets you find truth in randomness. Differential equations, which let you model basically any system in nature, weather, populations, epidemics, black holes. Linear algebra, which is the math of transformations and dimensions, and which is what every machine learning model in existence is made of. Do you want to know what ChatGPT is doing under the hood? It's mostly linear algebra. Matrices multiplying each other over and over and over. That's it. That's AI. fancy matrix multiplication. And then there's topology. Topology is where math goes when it has completely let go. Topology doesn't care about distances or angles or sizes. It only cares about connections. In topology, a coffee mug and a donut are the same object, not metaphorically. Literally the same, topologically speaking, they both have exactly one hole, and you can deform one into the other without tearing or gluing anything. Topologist is someone who can't tell the difference between their breakfast and their morning coffee cup. This is not an insult. This is a career. Topology gave us tools to classify shapes in any number of dimensions, including dimensions we cannot see or visualize. And when physicists started asking questions about the shape of the universe, not what's in it, but what shape is it, topology was already there, waiting with the right language ready to go. This is the part where you step back and realize what happened. We started with fingers. We ended with the shape of the universe, and we didn't jump. Every step grew out of the last one. Tallying needed place value. Place value needed 0. 0 needed negatives. Negatives needed irrationals. Irrationals needed imaginary numbers. Imaginary numbers needed algebra. Algebra needed calculus. Calculus needed everything else. It's one unbroken chain from a baboon bone in a cave to a physicist describing the curvature of space-time. The same instinct. The same move. Look at reality. Find a gap. Invent the thing that fills it. And here's what math actually is. It's not a collection of rules someone made up to torture you in 7th grade. It is humanity's most precise language. It is the only language where you can say something and be completely, provably, forever right. It's in English you can argue about what a word means. In math, the proof either works or it doesn't. That's it. No room for opinion, no room for spin. Just truth, built from nothing but logic. The universe seems to be written in this language. It's either a breathtaking coincidence, or it means something very deep about the relationship between thought and reality. Physicist Eugene Wigner called it the unreasonable effectiveness of mathematics, the fact that math invented for pure abstract reasons with no practical goal keeps turning out to be exactly what physicists need. Imaginary numbers, non-euclidean geometry, group theory, all invented as games, all drafted into service by reality later. So here's where we started. You have 10 fingers, that's why math exists, and here's where we land. Does mathematics exist because humans invented it? Or were we just discovering something that was already there, waiting in the structure of reality itself, before any human ever picked up a bone and started scratching? Nobody knows. That question is still open. And honestly, that might be the most mathematical thing about it.